Okay. Hi everyone. Happy Friday and thank you for joining us today. Today we are honored to have John. Like all of us, we know him, and but of course I'm going to read his bio. It's very short. So with degrees in geology and oceanography from Oxford, Southampton, and Dalhousie, John has always had an underlying interest in seabed sediment transport. For the past 40 years, however, he has been working primarily with assessing and improving the performance of underway acoustic seabed and water instrumentation, multi-beams, sub-bottoms, ADCPs, and facial sonars. These tools are, of course, one of the prime means of monitoring the seabed and oceanography. He is in the process of winding down his full-time commitment at CCOM, but continues to be interested in those field programs that perhaps incidentally study beautiful bed form fields. Please join me in welcoming John.
Oh, thank you for staying around on a Friday afternoon. And as you mentioned, I'm sliding out. I'm officially retired, which is fantastic. So I can become old man and just tell stories. That's kind of part of what I'm going to do. This project that I'm describing, I have never been funded to look at a sand wave. But I love sand waves. If you don't, oh, that's your region. But sand waves are a remarkable feature. They're not stationary, they move, and they're a challenge to surveys. So many applications, and I'll show you there are real reasons to study them. But there's a project, it's actually part of our new grant. The new 4 NOAA ships have all the instrumentation, and they could just do hydrography, but they are capable of simultaneously looking at oceanographic circulation and seabed change. And there's a lot of applications for that. It's actually also the multispectral part of that is funded through ONR, and CONSPO very kindly funded the field program. And this actually builds on work I've been doing over the past 20 plus years on sand wave fields. But I'd like to sort of start 150 years ago. You might think, well, what are we doing? Let's get into this century. Well, it's 2 centuries ago. And the Challenger expedition was remarkable. They didn't have the benefit of acoustics, but they had multiple sensors. People know it well. You know, this guy got an abyssal plain named after him. This person got a deep sea ridge named after him. But the hidden success of this was actually the surveyor, the navigating lieutenant. He's just in the back row there. My personal hero, Tommy Tizard. And this was as a young man, but he basically, in classic chief scientist, you know, go over there, make my measurement. But we, the mapping community, have to actually do it and do it right. And he ultimately became the hydrographer of the Navy. And so one of his last things, which he actually published in Nature, I don't think I've ever seen a civil servant publish in Nature before. The challenge at the time was the approaches to the Port of London, from which the shipping went to the rest of the empire, and getting it out, turn right, go out the channel. And unfortunately, it's a very, very shallow macrotidal environment. They have to cut through a channel, the Duke of Edinburgh Channel. He compiled 80 years worth of surveying of this channel. This was all horizontal sextant. But over an 80-year period, the channel significantly migrated, it shoaled, they tried to dredge it. And think about the positioning challenges. Just with horizontal sextants, thick fog area, you have to build towers on intertidal sandbanks. But the article is fascinating. He actually was looking at why it was changing. This is, of course, is an estuary. It's a sediment transport problem. And today, you might think it's irrelevant, but that sandbank is actually a 600 megawatts, part of the London Array. And it's extremely relevant today, and they're continuing to survey that just with shining authorities. And but underlying it, what's driving the sediment transport? He had the capability to do bathymetry to see the sandbanks move, but current measurements pretty hard, especially in those days. I got into this game about 30 years ago. You might not realize it. The gas field, the gas that you're getting here in New England is primarily coming from the Sable Offshore Energy Project. And there's a gas pipeline that goes from seaward of Sable Island into Nova Scotia and then on land. And they were surveying this about 30 years ago, before the winter, after the winter, before the winter, after the winter. And in fact, if you look at the backscatter part of it, go backwards and forwards like this, remarkable change. And they were concerned because they have to put a gas pipeline. It's about a 24-inch diameter, and the survival of a typical offshore structure, 25 years. So it's got to sit there. It's exposed to open ocean gales, and we have to understand the erosion and deposition, how it's going to impact infrastructure, whether it's oil field or gas field in this case, or there are many, many other structures as well. And again, what's driving the sediment transport? So we need to make measurements of the circulation, whether it's tidal or wind or wave-driven circulation. And of course, wind farms have exactly the same problem. It might be a little bit on pause at the moment with this administration, but it'll come back. It's enormous in the North Sea and in the Baltic. And the issue they have, of course, is scour. And there's a requirement to survey all the cables routes, all the bases of all the foundations, at least once a year, whether you're in the UK, the Danish, the Dutch sector. It's an enormous issue. But behind it all, we actually want to measure the circulation as well, not just react to a scour, predict the scour. And again, life of these structures is typically 25 years is what they plan for. But yet another structure, again, what's driving the sediment transport? But the areas I've been working is at UMB for 20 years or so, Bay of Fundy, macrotidal, largest tides on the planet, but also for the last 10 or 15 years, the Salish Sea, the Strait of Juan de Fuca, Georgia Strait. And in both of those locations, within the last couple of years, what we've had is these are the O2 systems. They're 2 megawatts of floating platform. They're going to put them in Rosario Strait, funded by the state of Washington, or they might, I'm not sure if they still will. And most recently, Nova Scotia has gone ahead. They're going for it. Fabulous. And so now you've got a reason to do this because, of course, they're deliberately in high tidal streams, which are going to have tremendous sediment transport issues. The Bay of Fundy, highest tides on the planet, Reef Basin, that's still in Canada. And of course, you need a constriction to get above 2 knots to be very, very efficient. And so that region there, why were they there? Well, again, because of the constriction. If you look at it, if you do a multi-beam survey, you've got these sandbanks. You've always got a pair. There's one here and there's another one there, what's called banner banks. And so where are they going to be? Where are they going to site the power stations there? There are these hydrodynamic models. This is a barotropic model, but honestly, the Bay of Fundy is mixed top to bottom. There's barely a density contrast. And they pick a spot, but why are these banks here and on the other side again? And what we're seeing is the tidal currents, but it's the residual transport integrated over a tidal cycle. In this case, it's M2 dominated. So they proposed them. They actually built them. It was very embarrassing because I think they lasted about a month. But now they're going to put in those Scottish systems, which hopefully will work this time. So let's try and understand these headland-associated banner banks. They're beautiful. You'll always see these pairs all over shallow tidal seas. So the Bay of Fundy, they're everywhere. Constrict, have a headland, have an island, any money of them. You'll always see pairs of them. And wherever you constrict flow, you accelerate it, you've got more energy there. The one we were looking at, of course, is the Minas Passage, but that's St. Martin's. Again, look at the headland. You've got a pair of banks on either side. Of course, you can see the sediment in there. It's generally really well sorted, coarse sands, excellent aggregate for construction. And let's look at another couple of headlands. Again, they're just beautiful. And you see these pairs of them. These are dynamically stable. They've been there. I've been surveying them for 30 years, many of them. The outlines are identical, but the bed forms are continually migrating. They're dynamically stable. What's holding them there? It's really the residual sediment transport. So this is the one we focused on. This is close to the approaches to the Port of St. John. The gas terminal is here. So, of course, they're very, very interested in erosion and deposition there. And a thesis about 20 years ago, we'll find a mouse to click on it. Oh. Anyway, trust me, it moves. So it's good. We did, Garrett actually did 6 surveys. You got continual migration of those bed forms. And the question is, what's driving that? So this repetitive surveying, we want to understand that. And I've used this. I've never been funded to look at these. But in order to test the integrated performance of a system, I want a short wavelength target, nothing better than the crest of a sound wave. And it's just, if you happen to go back, they're going to move. And so that you can really look at bed load sediment transport in this situation. This is not new. Back in the 70s, Robin Pingree really first proposed this for the Shambles Bank off the south coast of the UK. And what he was looking at, he made no observation, but he knew about the flow. And as you go around a headland, you've got a gradient in flow, you induce vorticity, and the net result is you get residual circulation, a pattern that looks like this almost every headland. That isn't the current. What that is, for example, there you see the current, the ebb, and then the flood. That's very characteristic, these ellipses. But averaged over a tidal cycle, you see that little arrow there. A grain of sand will move maybe 100 meters that way, it'll come back 100 meters, but if it comes back 98, there's net transport in one direction. And so this is looking at that. Of course, it's grain size dependent because there's a bed shear stress threshold before they actually move. But as all these banks, there's really rapid flushing of sediment on the inside of it, goes into suspension, and it comes round again. And you have these two banks. They could be asymmetric depending on the shape of the headland. Actually, Coriolis has a small effect, but friction dominates for these situations. So we understood in principle to actually measure a current field on a large area like that is actually surprisingly hard to do, because if you start steaming, the current's changing. You've got 12.42 hours to complete an M2 cycle. So this was done, I think the first time it was done was Rocky Geyer and Rick Signell at Woods Hole, and they were just off Martha's Vineyard. There's a constriction, there's a headland, and they've come up with this residual circulation pattern. But how did they do that? Because you can't be everywhere at once. You can put an ADCP down for a month or a year if you like, but you've only got the observation there. So you want to be everywhere. So what they did, they actually did 6 surveys. They basically beat one area to death, came back on the same phase of the M2 tide, and it didn't matter if it was a day later or a week later, be careful to be springs or neaps. And so they actually, over 8 months, they covered the whole area. So it's a real challenge to make observations. And we're lucky now, we've got these hydrodynamic models, but you've got to be careful not to trust them necessarily. We can still use our ADCPs to actually see how well they perform. So I doubt this animation will play either, but let's try it. Actually, click might make it go. There we go. So what we're doing here is basically we steam around a circle, around one of these banner banks for 12.5 hours, which is really tiring when you consider you have to get there for an hour and a half transit, go back for an hour and a half transit, drive to it. That's a 16-hour day. I'm too old for that. But we used to do that. And what we do is for each one of these, of course, we look at the ellipse, we actually map the residual. And Garrett, I sent him out 3 times. And you come up with a picture of the residual sediment transport in the area. And again, it's interesting, the sort of minimum sediment transport is offshore, but all this stuff, the bed forms are asymmetric, moving in that direction on the other side of the bank, and they tend to be pretty much symmetric on this side. Remember, it's always reversing flows. And actually, if I can do the animation again, what was interesting here, back even more, this is the plume of the St. John River, which isn't present, then it's present. So what we started to realize is we had to use baroclinic models, especially on the West Coast where you've got the plume of the Fraser River, because there's a lot of shear in the water column. And so going from the East Coast, which is macrotidal, it's about 7 or 8 meters. Well, in that location, it's actually 14. And go to the West Coast. The trouble with the West Coast is it's a mixed diurnal. As you can see, there's diurnal and semi-diurnal components. And throughout the lunar cycle, you see the importance of the 2 changes. It's very easy in an M2 dominated environment. You can do there, you can come back the next day. If you miss it, you can come back on the next spring tide. Basically, things are the same. Here, the trouble is you now have to be out for 24.5 hours, which is stupid tiring. And the question is, are you in the same world here? Because it may be a smaller amplitude, but now that you're M2 dominated, the rate of change of elevation is higher. So you've often got higher currents, surprisingly, on a neap tide, whereas these diurnally dominated springs. And so it's a lot harder to do it on the West Coast. So if you're operating, this is one of the West Coast bedform fields, repetitive surveys. You can see we're going neap, springs, neaps. And you now, with improved multi-beams, we're not just seeing the big bed forms migrate, we're seeing the smaller dunes on the back of the bigger dunes. So you can really get a good feel for the residual sediment transport. It really is residual. Just because you see everything going to the right doesn't mean that it's a unidirectional current. What you've got again is you've got reversing currents, but in this particular location, the residual transport is in that direction. But we've actually got to come down. When you build a piece of infrastructure over a sand wave, it's not the fact that the dune is moving that way on average. Yes, it'll bury it and expose it every couple of months. It's the fact that it's like a piece of sandpaper just grinding away at your infrastructure if it's exposed, and that's where the damage is. So what we're starting to do in this area is actually image within the tidal cycle. So here we're looking at just the flood stream, and actually in the water column, you can actually see at the peak of the bed shear stress, you actually see the sediment thrown into suspension. And as the tide reverses, you see it chucked up in the other direction. So it was a bit of a surprise. It was incidental. This was testing for NAVO, actually. It had nothing to do with sediment transport, but we were really surprised with what we're able to see here. So what does it actually look like? If you actually take a look at those two surveys, one that's, of course, done on the flood, towards the end of the flood, and the other towards the end of the ebb, you can see the crests are reversing just within a tidal cycle. And if you take a difference between the two, as well as the crests flip-flopping, you actually see the bed forms on the back of them. And so this is actually of great interest. It's not just burial exposure, it's the fact that we're basically building, whether it's a pipeline or a fiber optic cable, if you lay it on the top of these dune crests, you're actually better jetting it in to avoid this grinding motion. And one we also do then is, why stop there? We're actually, let's look at through the flood tide cycle at 11 o'clock, 1 o'clock, 3 o'clock, and you can see the reversal of the crest. Within the first 2 hours, what happens, the top of the crest, which was very asymmetric, is blown off, and then it starts to grind back. So we're now getting much more detail. So as well as over a month's time scale, the dune move in this direction, you've basically got this flip-flopping backwards and forwards from flood and ebb. And it's really interesting to see that. It changes the habitat as well. This is a sand lance environment. So what I was doing on the west coast, everything I've shown you today were actually very shallow dune fields, sort of in the less than 20-meter range. It's not really a challenge. But the west coast is heavily glaciated. They're basically drowned fjord systems. I'm looking at banner banks now that are in 70 to 120 meters of water, sort of 5 times deeper. And I still want to see the small dunes move on the back of the big dunes. And that was the challenge. A couple of days ago with Kongsberg, I was talking about all the integration issues you have with this and trying to operate. It's not just the multi-beam. We're operating ADCPs at similar frequencies, and we're operating multiple frequencies of water column imaging. We actually want to see Kelvin-Helmholtz waves. You can see turbulence on the shear horizons at the same time. So the issues for us is, from a hydrographic point of view and for resolving dune crests, I want very high along track density. And that's a concern when I start grouping. I'm firing other sonars and I have to wait. So that's something that we're really working on now. The other thing is, when you're deep, generally your systems go to much narrower bandwidth, poorer range resolution, just to track. So you can see the big dunes, but you can't see the detail. But if you override it and you actually force it to the high bandwidth, you can actually see the detail, even if you are at 100 meters. So in doing so, you have to sacrifice swath width. You're doing this. But I basically want to see which way these guys going through a tidal cycle. And it's all, again, driven with CCOM funding by the 4 new ships. They've got everything. They've got 4 ADCPs. They've got 6 fisheries sonars. They've got 2 or 3 multi-beams on board and a sub-bottom profiler. They've got everything. And so one of the requirements, or one of the things of interest, is these operational forecast models. I hope you'll listen to Natalie. I think she's given a talk on Tuesday, isn't she? And basically looking at this, this is a University of British Columbia model, but there's a really nice NOAA model as well. And you're looking at the plumes of the rivers, the Fraser, and the area we're actually focused in is where the constrictions are, Harrow Strait here, and it's Rosario Strait where the tidal power is going to go in. So if we blow up that area, it's heavy shipping lanes, which is kind of interesting. I use my favorite vessel, the Herons, 10 meters. It's a Canadian government vessel, and we have almost everything on board, which creates all sorts of problems, which are great to solve. But if we survey in this area, you can see that's the deep of Juan de Fuca. The water comes around, there's a shoal here, a sill, and then it goes up into Harrow Strait, up towards Vancouver. And the University of British Columbia have this amazing model. You can just go and download it from Amazon. Every 12 hours, they update it. They'll give you predictions 7 days into the future and a nowcast. So I grab it. You're just seeing the surface salinity. You're seeing very thin plumes from the Souk River, the Elwha, the Dungeness. But the really big stuff is actually coming through from the Fraser, and it's basically being shredded as it goes through the Gulf Islands. It's a much, much thick layer. And the dune fields I'm looking at are on these headlands. They're basically banner banks on either sides of the headlands. And so this is the area I'm going to be focusing on. So just to show you, or just off Oak Bay. So it's a challenge. The area is right in the middle of the shipping lane, so you have to get out of the way. They don't stop for you. And fortunately, the Canadian government has got multi-beam for everywhere, so I can check what it is. You can see this is a gorgeous, really big, it's one of the biggest dune structures we've got in Canada. There's a shallow water dune field here. That's the one I'll show you today. And those are the targets that I've been operating on different water depths. And of course, you can see that it's an accumulation of sort of a coarse sand up there. This is actually very, very different bed form field. We assume it's a gravel pavement, but again, here, this nice little lens there. They're all banner banks, but a very complicated circulation. So if we go and have a look at this, it had only ever been surveyed once before. And you can see, obviously, no surprise, over 18 years it's changed. But it's very, very active. On this side, there's net migration in this direction. They're asymmetric. On this side, they're almost symmetric, but it's actually blasted through here. You can see it's very high backscatter here. And this is the area I'm going to show you as an example of what we can do. So my interest, when I first went out, this is just September last year, I did the whole survey, but running the ADCP, a conventional survey. But thereafter, what I want to do is I repeat a cycle over the dune field about once an hour and repeat it as I go through a tidal cycle. And the trouble is, of course, I started in the neap tides and I ended up in the springs. This is M2 dominated. This is sort of K101 dominated, unfortunately. So there were the 4 surveys. And sometimes I managed to get 11 sections, sometimes 5. The gale blew us off there. And this last day, we actually got the nicest results. So the idea is you can't go everywhere all the time with an ADCP. You just have to accept that. But what you can do is make the observations, confirm it to that model, the UBC model, and then you can look at the migration, not just of the big bed forms, but the smaller bed forms on the back of the big. And that's about 95 to 75 meters over the top of the crest of that banner bank. So I just want to show you some of the depth changes. So that's the dune field, and I'm just going to pick out that corridor because we always ran that every time. So we're looking at the 4 surveys, and you'll notice sometimes it's really high res, sometimes it's not. And that's because I'm actually varying the pulse length, because it's all very well, if you want resolution, you go high bandwidth, you resolve the bathymetry, but the noise in the water column is terrible. You can't see anything. And if you go the other way, if you put a nice long narrowband FM pulse, you can see the circulation in the water column, but it's a little fuzzy. It's way in spec. But what we're really interested in, it's not the big ones, they're obvious. It's these guys that I'm interested in. You can see their resolution is variable depending on the swath. So that's 4 surveys. So I have 3 differences. So we can actually do the first difference, the second, the third, just cycling through them. And you see sometimes it changes and sometimes it doesn't. Trying to work out, is that a resolution issue? Is that actually a process? And sometimes actually we just stop it. First 3 days, this is the difference. What you see, obviously the big bed forms are moving. That grayscale is plus or minus a meter. And the differences are about 30 to 60 centimeter height change, well beyond IHO special order. But it's these guys that are interesting. You can actually see those moving, and the change is less than 10 centimeters, and we're in about 80 meters of water. So it's not just, it's resolution, it's lovely, but there's all the boring things we have to do, integration, patch test, but it's all there, but very, very necessary. So with the high bandwidth, the trouble is you're very susceptible to noise. And so all sorts of mistracking. So talking with Kongsberg, they're basically going to give me a high bandwidth FM pulse to see if I can improve it. But you can obviously get rid of that. now you've got a best representation of the seafloor. The second one was also that, it's just a single swath, so if you just jump between the two, hopefully you can see that the dunes move. And what you're seeing is the bigger ones, they do shift the scale of it. They're about 30 to 60 centimeter change. They're really quite steep crested. The total amplitude of these waves is about 3 to 5 meters, wavelength 70 to 150 meters. So not a big challenge. But superimposed on it, there's these smaller bed forms. These are the ones we're interested in. This is the challenge. And what we're seeing there, and they're much shorter, they're about the length of the table here, maybe a little bit longer. And their amplitude is just about, that's crest to trough. And we're seeing changes down at sub 10 centimeter range. It's really nice that we can see it in this case. What's interesting though, is over that 3-day period, I see a net migration in that direction. And that's actually, over long term, I can see these are asymmetric. I know they're going to be going that way. It's not a surprise. The smaller guys, though, actually go off obliquely. The secondary circulation, you've got these two ridges, the circulation on the backs of them often diverges significantly, and you can see the direction of those migrations as well. Well, let's jump to the next 5 days. And this is a little worrying. Now, all of a sudden, all the dunes go backwards. And is that because the regional circulation is backwards? And I think all we're seeing here, because it's such a short period, the first one, I can go back to it. No, wrong way. Go back, there we go. You're actually just come out of an ebb and you're coming up on a flood. So you can see there's a net change in that direction. Whereas on the next tide, people get this wrong. I have to hold it that way. What you're doing, you've just completed a flood and you've just come out of an ebb. It's very early on in the survey. And so all I think I'm seeing is this, but that actually probably reversed 1, 2, 3, 4, 5 times in that cycle. And so what we're actually seeing, if I'd been able to put in surveys more frequently, I would have seen that changing on a sort of a 6.5 hour time scale. But what we get into now, the differences are still pretty good, but I can no longer see these bed forms move, which I find quite fascinating. They seem to only move in one direction. And why is that? We can compare the two surveys. I am worried that the second survey is lower resolution, that's a lower bandwidth, but you can actually still see them. And so if I go backwards, forwards, I think you agree, it's not a resolution issue, they really aren't moving. So it's kind of interesting that the secondary bed forms don't tend to flip so much. They're actually going in the same direction. And again, I'm not sure, this was all sort of first to access. In the third 3 days, where we just come out of the spring tides, it's starting to think about the M2 component, you see almost nothing. And I think that's because we just finished a flood, and at the end here, it's off the end, we just finished a flood. We're actually at the same phase of the time. So it's kind of interesting, learning a lot, but from operational point of view, we're testing the performance of the systems. What I want to go on to now is looking at the imaging in the water column, because this is just the bathymetric differences. So what I do is I repeat this circuit. It's this survey, so actually 11 lines it took me, and you can see we're just stepping through the survey to build up the terrain model. And if you look up the top, you can see the tide is rising through this period. And it's kind of overwhelming, but the ADCP provides you with total current magnitude. These are the flows if they're going, I've projected everything onto a common axis. So that's going in that direction, it's actually an ebb. Then you'll see the early flood coming in at the end of it. There we go. It's actually you can see there's actually incredible shear. And right at the end of the cycle, you'll see this incredible structure here. The water column imaging, I'm looking for evidence of anything. And this, unfortunately, I'm using the really high bandwidth. You can see nothing there. But the low frequency system, you can actually see what's going on. So I'm just going to freeze it. Late in the tidal cycle, all of a sudden, you see this structure come in here. And that's, I think it's 125 meters. It's about 20 or 30 meter thick layer. This is actually a plug of the Fraser River water. And it's an incredibly steep tidal front. And you can see very different velocities. It's going this way, it's coming this way. That one's actually starting to move while it's still shearing underneath. And that's a 4 meter a second sound speed. So from an operational point of view, it's very important to understand these tidal fronts. And I'll show you, we can see that in the hydrodynamic model. Just an hour later, it's now much more developed. You can see the structure there. You can see the head of it. What's interesting, almost always at the head of these structures, you get massive downwelling. And on the inward side, there's upwelling. As I'm going to show you, the biologics just live there. It's on the, you can recognize it. All the local fishermen know where these are. So let's move on to the second survey now. And we're running the center and then that funny three crosses, center, funny three crosses. And again, we're doing a different phase of the tide now. If I can get that, show a falling tide, there you go, it's falling. So there's really the thing that I also see, and I really didn't expect it, just at this point here, if I freeze it, now all of a sudden you see these bright zones on the crests of every wave. And at first I thought this was a noise problem in the sonar system. I thought there was some, the GVG was, because it is adaptive, it depends on the bottom backscatter strength. I thought that was the issue. As it turns out, that's actually sediment generated noise. The gravel itself is moving and you can hear it. And well, that's my theory. I've seen this up in the fjords on the turbidity currents, but I hope I'll convince you. And this summer now, the 26th, I'm going to be putting hydrophones out to try and prove my case. And what's really interesting about it, most of the time the high velocities are up at the surface, but whenever you find that you've got that constriction, there's actually the tidal front there, the high velocity flow drops down to the seabed, and that's the only time the bed forms move. So it's not that they're moving a little bit and then a lot, they're basically stationary until this tidal front comes, and then this big surge comes down. And so you see them there. So again, I'll show you this and I'll show you it in more detail. So now let's look at the plan view. So again, the same region, we're in this zone here. And what I want you to notice at a certain phase of the tide, now you'll see this burst of light colored water. What that is salt water. It's a heavily stratified system here. The whole of Strait of Juan de Fuca is an estuary. The brackish water is going out to sea on average, and the open Pacific waters, cold waters are coming in. And the whole thing's tidally pumped. But wherever it goes over constrictions, you get massive upwelling. And you'll see these, if I actually just freeze it, it's just about to start. You see it off Race Rocks, off that headland there. And then you'll see it picks up, it develops, and it actually comes round Discovery Island. And the bedform field I'm going to show you is sitting there. That's actually the tidal front, as resolved by the regional hydrodynamic model, which has got about 500 meter horizontal spacing. And now you see it very, very clearly. This is part of the reason that that bedform field sits there. And it's also incredibly biologically productive. All the whale watching boats from downtown Victoria either go to here or they go to here. And they do that because cetaceans are munching the fish that are munching the zooplankton, and the birds are eating them at the same time. It's very obvious. And those are the bedform fields. I'll show you number 2. That's the one I want to focus on. So if we now get in, zoom right in on Oak Bay itself and Discovery Island, we've seen this before. The thing to notice is there's the rock constriction offshore of Discovery Island. This is what's forcing the upwelling here as the flood tide comes in around here. But the model, the hydrodynamic model, there's always a limit in resolution. If you're going to go from one end of the Strait of Georgia to the other, about 600 kilometers, you can only support 500 meter resolution. So the model is forced by the atmosphere, the solar radiation, the cloud cover, the humidity, the air temperature, the wind speeds and directions. And it's also forced by the freshwater inputs of all the rivers in both Washington State and British Columbia. But the whole thing is forced on the model. It's actually got 41 layers. The upper 10 layers are between 1 and 2 meters thick. They're really focused on looking at the river plumes. So what they actually see, as far as the model is concerned, I just want to point out the islands, particularly this one, Trial Island here. The model, unfortunately, doesn't resolve it. There is a shoal at Trial Island. There is a shoal at Chain Islands. But so any model that you have, a coarse model, is not really suitable for detailed circulation, but it's getting the circulation of the whole Strait of Georgia and the Strait of Juan de Fuca right. So the islands are missing. So what we can do is, again, I'm just going to play you through. This is October the 4th when the nicest things happen, and you'll see at a certain phase of the tide, just going to wait for it. There we go. And if we just stop it just before it happens, it starts down here, just off the southern tip of Trial Island. And it's a really interesting place. It's an island, it's got a lighthouse on it, it's got radio beacons, and it's where the sea lions come. I now live in Oak Bay, and I'm woken up every night from December to February. They come here to frolic. Apparently they have bachelor parties and sing. And you can hear it at night. They're there for a reason. They're there because there's cold upwelling right off the tip of the island. They don't have to swim very far, and they're eating salmon. So it starts there, but within the next hour, it's moved off Discovery Island. At Discovery Island, you've now got that front developed there. And that front is actually very obvious if you're on the water as we survey it. When a cargo ship isn't in the way, you'll see all the wildlife basically sits right on the inside of the front where the water is upwelling. And so they know what's going on. I just didn't. And so the structure moves there. So now this is a model. It's lovely. It's animated. You might believe it. But what we want to do is actually put a vessel out there with a really good ADCP and see how well does this reproduce the actual circulation at that location. So what we also want to do, this is the surface. We want to cut down through the 41 layers and see what the deeper structure is this, because we're only seeing the surface. There's going to be, there obviously are picnic lines like that, but when you have a tilted picnic line, you've got a tidal front. That's both interesting to us as a sound speed problem because it's worth 4 meters a second. Oceanographically, it's really important. And it's controlling the sediment transport, as it turns out, in this situation. So what I've done is I've put it all together. That's the regional model there. This is the local model, and you'll see the little... That's us. Again, just to emphasize, you can't be there all the time. You can put an ADCP on the bottom if you like, but it'll only tell you the answer here, or here, or here. And so the great thing about a vessel-mounted ADCP is you can do sections. So along that black line there, we've got the salinity. You can see the blue is the low salinity Fraser River water, and you'll see it kind of pulses. Temperature matches it almost entirely. Same things, the predicted of currents, that's the magnitude. That's the along and the across section. That's the in and the out of the page. And these are the vertical, the upwelling and the downwelling. So let's just freeze it when things get interesting. So it's just starting to upwell off Trial Island. Let's get going. We leave the dock. It's about 6 in the morning. We're heading out. We're doing a survey here. This is where we're again doing the same ADCP process here because we're interested in the circulation on that shallow sandbank there. And the upwelling hasn't started. And in the next epoch, we go right through the front. So if you look at the front has not yet passed the section. So if you look at the section, you'll see the Fraser River water, or brackish water, it's about 1 part per 1,000 shallower. Is basically all the way across. There's a slightly tilted halocline tilting down towards Discovery Island. And circulation, you've still got, going out to sea, you've still got the last of the ebb here, but the flood is starting to come in through here, through the section. The surface waters, the deep waters are actually coming in like that, and going out like that, and the surface waters are starting to come across. But let's actually take a look at real observations along that line. So we're here, and it's quite by accident, but we steamed across. What does the front look like as we go through it? So this is just a freeze from that day. The one line, we had 2 cycles. You can see we're on the flood tide about 3/4 of the way up. If you look, you can see the water's fastest at the southern end as it's coming over the rock ridge. You can see, though, the fast water dips down deep. And in fact, the bottom is way down here, but it can't actually penetrate. There's a lot of turbulence down there. And you notice here, there's a very pronounced front here, and there's actually a less pronounced one here. If you look at the water column imaging, if you look at the EK systems, you can see the tidal front. This kelp is all built up along the edge of the front. You can see it there. You can actually see it in the CP300. It's an ADCP, but it's got a very long pulse. It's a very good signal to noise. You can actually see the water mass boundary. But notice that both the multi-beams seem to be corrupted for some reason. They've got these bursts of noise that don't show up in the other systems. But this is what I think is sediment-generated noise. So actually zoom in on that. I'm starting to realize how changing things were. We have an MVP 30, did you use a hydrocam or you haven't yet? You will, hopefully. It's got both temperature and salinity, but also optical backscatter. So we're dipping, you can see the profiles, it's warm water, and then abruptly at this depth, it gets both salty and cold. It's worth about 1 PSU and a drop in temperature about 1 degree C. That's about 4 meters a second combined. And it's not really clear. This is just the 710, which interestingly, every time you slow to do an MVP dip, look at the propeller noise disappear. It's kind of depressing. But the third thing that I've never seen before, this, again, it has 2 optical backscatter probes. I'm looking for evidence of suspended sediments. And for the first time, we finally saw it, always in that colder layer there. So what we have is basically, this is the tidal front. It's been held back here. The water here is coming over the sill, somewhere there's suspended sediment down here, and there's this cold, salty underflow. And so this is basically stemming the tide, and the first burst is forced down under this because of the density contrast. And for some reason, we're getting these strange noise effects in the multi-beams. And so the last line we did is we're coming out, we actually went up there, down around, and now we're crossing the dune field itself. And now you'll see, if we actually look at the black line, we should see the tidal front in there. But remember, our resolution is about 500 meters. And if you look at the top up there, you can see it. The model reproduces that front position very nicely. And I'm actually really surprised about it. I mean, you see very clearly the surface expression, but you also see that it's tilted down. It's basically a plug of brackish, warmer water as the upwelling Juan de Fuca water comes in here. So it's really nice. It gives us confidence in the UVC model. But what about the actual acquisitions? We go through that line there. So you can see we're coming across. It's a front here that's part of the Fraser River plume there. You can see it speeds up. These are the surface velocities. And there's a boundary right on the top of the bank here. And again, you see very clearly, this is the noisiest I've ever seen it at that location. And notice it doesn't show up in the ADCP or the EK80 data. There's something about having a broad receiver that actually makes you very prone to this noise source. And again, why is that happening? You've got these really high velocities and they're touching down on the top of the sandbank just there. It's just on that side, that is the east side of the bank that you're seeing heavy sediment transport. If you look very carefully, you can actually I think I'll blow this up. You can actually see plumes of sediment in the ADCP data. And this is, the line we're looking at is the line that's in the foreground here, and about 12 minutes later we cross on the back. And I find that really remarkable. This isn't a residual current, this is an instantaneous, just as the Fraser front is being shoved back and the first of the cold water is coming in. And if you look at all the vectors, it's incredible what's happening at that location. But it's the only time the bed shear stresses are high enough to actually make this noise. And presumably, I'm going to go back next year, now I know when to look to see if we can see the bed forms migrate at that location. So I wanted to finish by trying to look at that noise. And I think it's sediment-generated noise. I could be full of rubbish. Yes, I'm retired. But let's take a look. 100 pings. So we're doing about, I can't remember, about 2 hertz, so 50 seconds worth of data. And we're going across there. So notice at 712, you've got these 1, 2, 3, 4 really high noise zones. You don't see it in the 120, there's just a hint of it here. Remember, 120 is just looking within a 7-degree beam footprint. The 2040C mimics it somewhat differently. It's very different wavelengths. And look at the CP300. It's really nice, even though the range resolution is about 2 meters, it's rather poor. You actually start to see these big plumes of data. And what I want to do is just look at that 100 pings just as we go over that particular sand wave crest, because you'll notice the bright zones line up with every one of the sand wave crests. Remember that the crests is where most of the activity is happening. And this is, I believe, based on the GSC data set, this is sort of a 1 millimeter coarse, very coarse sand. Very well sorted if you could dredge it. So what I'm going to do is I'm just going to scan through those 100 pings. And the top is the 712, so 70 to 100 kilohertz. And the bottom is the 2040C. And at first, I don't think you'd really see anything until you notice the crest, follow the crest as it goes through to the other side. And you need a little bit of imagination. But what I'm going to be doing this year is I'm going to go out back to, now I know what's going to happen. I'm just going to turn off the engines and drift. And actually, Kongsberg are going to allow me to use their data element logger so I can have no noise and I can actually, at a megahertz, sample the full array to see that noise. So just to sort of, let's stop it for a second. See that noise zone there? It's pointing at this crest. It's the same on the 712. And at starboard side, there is the crest. Go forward to here. Notice that it's now in the middle. Let's go back. Work. There we go. Oops. Across. And notice in the background, the 2040 is much better at seeing these plumes of sediment. They're very localized. Stepping over, and I think the last one there. And so it's swinging through this. And actually, I didn't think I'd have enough time. I clearly do. But I would like to, I should have shown you, in fact, I showed you 10 years ago, we were anchored over a turbidity current channel in Squamish. And as the turbidity current comes down, you basically see this noise that follows the turbidity current. So I'm pretty sure this is what this is. And it's kind of a bit embarrassing. I was going out there and making a noise at all the frequencies. And if only I just shut up and listen. That's what my grandmother told me most of my life. And what's interesting is why are the crests making the noise? Well, what we're seeing is almost all the change, short period change, is happening at the crest. They're basically ripped off one direction. In hindsight, it's pretty obvious, but it always is. But there you go. And so these are really active. I'm really curious to listen to this. I'm going to be putting bottom-mounted hydrophones down there. I might not get them back because it's pretty strong currents. But just to sort of hear it, it's quite remarkable. The other thing I'll hear, of course, is all the shipping, because this is the main shipping lane into Vancouver. So I'll finish there. The sort of relevance, well, who cares? They're beautiful. I mean, if you don't think sound waves are beautiful, I just don't. I can't help you. In retirement, I'd like to make wallpaper out of bed forms. I think I'd make a killing. It's been gone. Has it? I'll tell you the story. But you just look around our corridors here. We have the most beautiful images everywhere. But okay, let's have some relevance. Shelf infrastructure. There's no, well, the dunes are beautiful, no question. But it's the wind farm scour that is driving a lot of the work in the North Sea. Less so in the Baltic, just because there's less tides, but there's still plenty of currents. And tidal power. I'm really excited. I'm sure Martin knows much more about it than I do, but this is really seems to be finally maturing here. But it's these operational forecast models. From the point of view of NOAA, they're producing these all over the coast, on both coasts and on a global scale. They look great. They're designed primarily for two things: surface heights for predictions and surface currents. That's what the mariner needs. But they're fully baroclinic. And so potentially this can help us, especially with our ASVs. This can give us sound speed fields. If you've lost your sound speed probe, how good are these? And that's what we can measure. It's something I think is really exciting. I think it's what Natalie's looking at. I think it makes so much sense. What's interesting, though, is it is a poor resolution model. And it has to be because it's a huge area. And so actually what I'm doing next week is going up to University of New Brunswick, Ian Church and co. They're really good at doing these nested models. So you have a regional model which predicts temperatures, salinity, velocities, and it's forced by the atmosphere, the rivers, the offshore tides. And what you can do is take those conditions and you can interpolate it on the boundary of a much finer grid over an area that matters to you. You're going to, I don't know, put a structure in that, I don't care what it is. And then you drive it. You don't even need to force it with the atmosphere because it's getting all its solar heating all around. And you can put in a much finer bathymetry. It still won't be multi-beam bathymetry, but maybe 20 or 30 meter grid, I would guess. And that's something I'm really interested in doing, to see if it can reproduce the circulation in detail over that dune field. Just go back. All part of this is, I think, yes, there's all this validation, but it helps us understand estuarine oceanography. because, the books tell us about the straight estuaries, but none of us have that. Puget Sound is a very complex estuary. There's an incredibly good model out of UW, I think, Parker McCready, I think the guy's name is. And this really helps us with sound speed and sediment transport. If you're charting in the North Sea, the MCA, Maritime Coast Guard Agency, decides how often all the areas have to be resurveyed. And that's based on sediment transport. And that's actually what Ian's doing. They've actually got a sediment transport component to the model. So if you get the currents right and you have the grain size right, you can start to predict net sediment transport. And I think the thing I didn't expect at all is this sediment generated noise. And it might be rubbish, but I'm going to be deploying. I have 3 of these hydrophones, which I was funded by Exxon for looking at turbidity currents in a deep fjord just 50 miles away. And we're going to be putting them down there. They can listen up to about 120 kilohertz, and hopefully that'll catch enough of the noise. I'm curious. Actually, we just heard the listens from Kongsberg sound very interesting. I think they can go up to 300 kilohertz. So I'll stop there if there's any questions.
Yeah, please.
John, thanks. Amazing presentation. I'm with you. I love sand waves, and I love, let's call them the proper names, subaqueous dunes.
Yeah.
But just a comment about your sediment-generated noise. I honestly think you're onto something there. When I had a look at where it was occurring and things like that, but as you see it propagating into the water column, I'm almost sure that's a gain effect.
Well, what it is if you actually turn off the transmit, it's a continuous noise and it's purely directional. I think that's what it is. That basically the beams are only listening here, they're not going to hear it until they're listening there, and it's not triggered by the shot cycle. The reason it looks slightly weaker towards you is we log R2 alpha R. We're not bringing it up as much.
It's propagating almost right up to the surface. I think that's a gain effect.
I wonder, but
I think it's a gain effect based on noise on the bottom.
Well, I was worried because the TVG from Kongsberg is adaptive, especially close to normal incidents, and I was worried that it was triggering it. But I don't know. We'll find out. Hopefully, at the end of this summer.
Very interesting, fascinating.
Tom, yep.
Great presentation. I'm still trying to digest all the work that you do. Really nice. So, why are those bands, those vertical bands, vertical?
Well, they're only
If the sediment is 1 millimeter in size, would you expect them to be suspended all the way to the surface?
It's not actually that there's no sediment coming up to the sonar. What it is if you just have the receiver, let's pretend this is the crest of the sound wave, that's making a noise. If you have a narrow beam system, you don't hear it until you're on top of it, and then you go on very quickly. With a multi-beam, you'll hear it at that angle, then this angle, and it's not that the sediment's coming towards you. I don't know, but I believe it. I should have brought in a little barrel of gravel or marbles and just shook it. This is pretty cool stuff, and it's making a noise there. And as long as you're listening, doesn't matter when you start, you finish, the noise is coming at you. So I honestly don't think it's coming up. The reason you're seeing it for quite a long time is when I don't just show you the nadir beam. I always average plus or minus 30, 40 meters just to give you a really nice clean image. So it appears much quicker in the multi-beam data than it does in the other one. But that's my theory, but I'm not.
Yeah, I guess I'm a little confused about the. Well, if this is noise generated, it's noise generated at the bottom.
It is, but
in the water column.
Yeah, but if it was a plume of sediment and I was pinging in it, I would get scattering off it, and then you'd see the shape of the plume. In this case, it's nothing to do with the transmission. It's purely I'm listening, and I'm still listening, but the sound was already coming at me, and it's never stopping. It's just a continuous roar. I've actually got recordings I should have played from the current. There we go.
But you mentioned to avoid the sandpaper effect for pipe, you jet it in. How far? You have to jet it in.
I don't know. I guess the bigger waves, I'm seeing the change is about 30 to 60 centimeters. It's expensive, I know, to jet. The trouble is, even if you jet it in there, over a couple of months, it'll be too late.
That was my question.
Yeah.
Such a range of
Yeah, Larry, the standard's normally 3 meters.
3 meters. Yeah.
I mean, I'm kind of hoping that as the wave goes by, it will drop onto the seabed and the next wave would bury it, and thereafter it'd be at some erosional pavement.
I don't think this they like the dropping on the seabed part.
Yeah.
With the wind turbines, bridge pilings, things of that nature, could they perhaps drive the sediment generated noise as well?
Well, there's no shortage of human noise and vibration. In this case, there isn't yet anything man-made there. I mean, if you had a tidal turbine, I suspect there's all sorts of noise involved with it. Yep.
Would a turbulent ejection or sweep events from the bottom of the surface with these, where you have flow field coming up, which pushes this, generates this W prime, which inverts upwards? Is that something that's resolved, or is that something that you see as noise?
It's, yeah, there's this, as the stuff comes off the crest of a wave, you often see the turbulent spins up into the water mass and takes sands with it, and maybe they knock at each other. I don't know. I think in the 20-meter example, I think I'm seeing stuff coming off the crest of the wave. There's actually another example I don't have here, that those giant bed forms. I definitely see this little entrail go up about 20 meters up into the water column. Here, I'm not convinced. I should have shown you the photograph at the bottom of the Heron. It had that much barnacles all over the hull. So a lot of the noise was actually my own, unfortunately. So I didn't have good signal to noise.
Is there a difference between when you record these measurements at high winds, high velocities near the bed, or when there are like a colder front that moves in and sweeps in, and the warmer front? Because
the change in the water temperature and salinity changes the sound speed, so it'll distort the surface. I don't think the attenuation coefficient hugely changes. I'd have to check that. I mean, it's subtly different. I'm just amazed how thick these tidal fronts are. Actually, that last front, as we went through it, I have no MVP dips after it, because we never dipped when we saw the seaweed on the surface, the kelp, and then we dip after it, and I put it right into the kelp, which is about 50 meters down. And unfortunately, it didn't break the cable, but it snapped all the internal connectors. It's only about $10,000. So, yeah. Yeah.
Great presentation. I was thinking about your earlier work that you did with Alec Hay and Matt Hatcher about sediment generated noise and turbidity currents. Yeah. So I like that you're putting hydrophones. I know there were some models involved. I'm wondering if you're thinking about comparing your hydrophone results to some of those collision models.
He was the first author on that. That was the experiment we did in Squamish. So if I get useful data, I'm going to email Alex. Yeah, it's not trivial.
No, it's
and it's actually it's very old. Peter Thorne did this. He had a metal barrel, and he just rolled it back in the 70s, and he showed you that if you had a mono grain size, it was really quite narrowband. But sand isn't.
I don't know if anybody else has done other sediment noise models. At least those are the two that I know of, but maybe.
I haven't looked at it for a while, but it was very fashionable, Peter Thorne and Alec, back in the 70s and 80s, 90s. I haven't seen many people do anything more with it. There's so much other noise. Bubbles are another problem that you hear, because they get released from the sediment. And then there's human noise and biologics as well. Yeah.
John, maybe back a slide or two. There's an animation of the water column, the 712, and the other sonars as well. Actually, would you mind going back to it real quick?
Yeah,
No, you have it.
Let me go back.
Which one? This further back?
Go forward one. Yeah, this shows it.
Yeah.
So the sort of ghosting right above the seafloor in the 712, is that the second swath?
Yeah.
And why do you not see that in the, or maybe the 2040C doesn't have a second swath?
No, it does, but they're closer together. That's why. This only needs to fire twice. That fires 6 times. That's why.
Yeah.
But yeah, that little flick up and down. If I want to get rid of it, I go to single swath. But then my long track density is twice as bad. So it's sort of gotcha every way.
Yeah. I saw it in our 712 and I wondered what that was. And then I saw it here. I was like, huh.
Yeah, I'm actually in the intermediate mode, the 0.7 millisecond pulse there as well, just to get better signal to noise. And that's why it's much more obvious. Yep.
it kind of looks like the noise, like the noise columns you're looking at, it almost looks like it appears, might be appearing everywhere. It's just that it's at the most like perpendicular points that it's following, which is might be why is that? Do you think that might
It's, well, partly there, you've got to be careful. On that, the top one is a 3-sector system, so you can see where the sector boundaries are. They're always weaker. There's more noise here. You don't see it so badly here. But the other thing is that the gravel is moving here, but I bet you it's moving everywhere. It's just more there. I don't think it's not moving. I think it's just the crest is where I'm actually I'd forgotten about those bursts. I think that may well be part of it. I'd love to.
And you think it's a clean gravel, that everything else has been removed?
I need to grab it. I'm not as strong as I used to be. I'd love to put bottom mounted ADCPs there, but we used to do it from the Heron, but I don't think I'd be safe anymore putting them down.
He brings up a good point. It is sort of the normal return to the seafloor as well.
Because where is the noise? It's here as well. It's possible that I don't know.
Yeah, it's
I
very
wish it was
subjective
cleaner.
assessment, but
And that's why we're going to drift with the engines off. And also remember, we tend to think about it being a really narrow corridor, but when it's just the receiver, it's actually listening. Think of the receiver beat patterns, plus or minus 10 degrees. It's actually quite broad. So there's other things in the field of view and maybe side lobes. I'm not sure.
Okay,
That was
That was a fantastic presentation. You had mentioned that the 80 hertz MBES was most susceptible to this kind of noise. Why do you think that is?
It's generally lower frequency. The props are cavitating, and most of the prop noise, I mean, the primary noise is actually really low. It's in the RPMs, but the noise doesn't seem to propagate up much above 100 kilohertz. It's amazing. We can go really fast, and the noise in here is unaffected. This is 300 kilohertz. This is very sensitive, and it would help if it didn't have barnacles on the receiver as well, because that's just a flow through it. But even that, this seems to see through the barnacles just fine.
Then Gates suggested that I roll up stuffed bubble wrap on the backside of the transducers in the gondola for the 712 to try to mitigate the noise. Maybe you should shove some bubble wrap.
There's a number of things I need to look into for that. There's certainly no question. Yeah. And it gets even worse. The year before, I had the whole EK suite there, and the 38 kilohertz is by far the most sensitive to noise. The lower you go in frequency, it's all about flow and props. The higher you go, it tends to be electrical noise somewhere in the system.
Any last question? Okay. Yeah.
Basic question. How loud do you think that signal is? What are the decibels on that that you're picking up?
I need to do my reduction. I don't know in the moment. It'll be kind of curious to see. With the hydrophone, I am able to bring it. Hopefully I can tell you in September. But I don't know yet.
Okay, yeah, with that,
Welcome, Danny.
So there's lots of work done with smaller scale bed farms on vortex dynamics and instabilities and all kinds of interactions between the flow and the shape of the bed farms. Is anybody working on those active models to reproduce what they might expect in a sediment transport model that might reproduce some of the behavior around these large bed farms?
I suspect there are a lot of people doing it. I just don't know.
Not with this group that you're working with here.
Here, no, because it's all hydrographers. It's not their day job. Alec Hay was doing that short range. Pete Tchaikovsky, I think, is at Woods Hole, was imaging really short wavelength. I don't know if they've done CFD on a few square meters on the seabed.
Well, Diane and her groups have been doing a lot of things here with sediment transport dynamics over bed farms. Savannah was recently doing that using PIV, but these are small scale oscillating conditions. Anyway, you've got the conditions that are much larger scale.
Yeah, it's a harder problem with storms because you have to be there when the storm is, and small boats and storms don't do as well.